All right. So let's continue. We have a lot more to discuss, a lot more fun with the convolutional neural networks before 9 we have to finish. So if you haven't finished the hands-on part, continue it at home and come back with questions during the office hours. So we have two questions here. One is online. What are the use cases for edge detection? Edge detection algorithms are used a lot in image segmentations, and so examples of that, I showed you a biomedical example. You can use it for detecting cancer and finding tumors in the images, in MRI images, for example, or you can use it to find cars and people and cows and dogs in the street when you're building self-driving cars. All right. The other question here is
complex numbers on the kernel.
what is the intuition for using complex numbers? Where is it? I put it somewhere. Oh yeah, here. Why are we using complex numbers here? So we have an operator that operates in the x direction. We have an operator that operates in the y direction. We want to do one matrix multiplication that does two at the same time without mixing them. So that's why we do it this way, and it separates the two because this is a linear sum. It separates the real part from the imaginary part. The real part is in the x direction. The imaginary part is in the y direction, and then we square them, we add them, we take the square root to combine them at the end. So that's it's a nice trick.
So this is applicable for Sobel also, then?
Yes, and it's one of the exercises that you do. All right. So Convnets, and I like Convnets better than CNNs because CNN is a thing, but Convnet has all the information in it. All right. So usually when you look at, and someone asked why I showed UNet, this is another architecture. And there are many more architectures that use convolutional neural network. What you need to know is that you have a lot of layers. You start with an input, and then you keep adding a combination of convolutions, pooling, some activations, and then every pooling and every convolution comes with information about the stride, the size, and then you go all the way to the end where you have the dense layers, where you do your. Oh, thank you.
I'm trying to force you at this point.
Thank you. It worked. Reinforcement learning.
I should shock you next time.
No, this works really. So we want to understand how these things work. What you do is that you start with, and let's concentrate on the images for now because they are easy, and we can imagine what is going on. And Reza next time will tell us about the text version of this. So we start with an image, and then we build a convolution layer here, and another convolution layer, some pooling, and then we do a lot of layers like that, and then in the end we have a classification problem. All right. Now what happens here is that we have, for every convolution, we have the values of the convolution kernel that we have to learn. No one tells us up front. All right? So we start with random values in our kernel. Lots of it. Like, for example, I think if I remember correctly, in AlexNet we have around 6 million parameters that we have to learn. Lots of parameters that we have to learn. And values of the kernel is one of them. And we do the convolution and we do everything else and we go all the way to the end, and then we say, okay, so what you saw here is actually a dog. And then we say, all right, so this is not right. We propagate back and we go back and change the values of the weights, and then we repeat it. We will see this next time, the mathematics of finding the solution, until we converge. And when we converge, for every layer that we have here, we have some weights and activations that are acting on our input until we get to the final part. What happens? And that is one of the, so during the lunch and learn, the first session, the 0th session that we have, someone asked about explainability. This is the first step towards that goal. Let's understand what is going on here. I'm not going to teach you how to build a convnet in PyTorch. You will do it after the class using the tutorial. It's very easy, you'll see. We want to understand what is going on here. All right. So the first layer, when we look at what the first layer saw, what the first layer learned, we see that actually the first layer is learning to detect. What is it detecting? Edges. Isn't that amazing? What we did, the first layer of a convolutional neural network just learns to detect edges. That's it. Yes?
Even without using the Sobel?
No, it learns Sobel or whatever it is on its own. And as you see, it is learning to detect the oblique, what? Diagonal, horizontal, vertical, all kinds of edges. All right? That's the first layer. And then let's look at the next layer. The next layer is putting those information together and is doing a lot of interesting stuff. It can, so these are the activations, and this is what actually in the images are triggering these. And this is what we can detect with those. So patterns that are edgy, like these. And yes.
Sorry, what is the left-hand side again?
So these are the weights and activations. Like I look at this layer and I say, what is firing? So what in my weights are the max? So I pick the maximum weights that are causing the activation in my layer, right? And then I say, what weights? What does it look like? What is it detecting? So these are detecting patterns that have edges in them, all right? Mostly these. And then they are putting a lot of edges together to detect things that are round, right? And we are still on the second layer. Yes?
So in order to do this explanation, you took the image, ran it through layer 1, you get an output, run it through layer 2, and then you can see the connection.
Yes.
Okay.
Yeah. And I have the paper for you. I'm sharing the link of the paper. Read it. It shows you a lot more examples about different architectures here. All right, so layer 3 is detecting patterns that are more than just one edge. So it can detect this kind of patterns, and more complicated stuff, and faces. See, we have started detecting faces. We can say there is a face here, and this is where the activation. This is what is seen in the. And layer 4 starts detecting animals. So it can tell that this now I'm looking at a dog, and so it's clustering similar images together because they have similar patterns. Remember, we started by detecting edges. That was the first thing that we did. And then we passed the information of all the edges that we discovered to the next layer, and then put them again together and got more. So you see that it has started clustering different kinds of animals and things together, and things. This is layer 5. And it looks like beyond this, we have all flowers in one category. We have animals. We have birds and things like that. All right, and then we pass this on into dense layers, and then we do a one hot or whatever we are doing with that. Done. You know how convolutional neural networks work. And you know better than a lot of other people because you know exactly what happens in the first layer. And you did it by hand. And you saw it was so easy. What the system does, what the network does, is that it learns those weights automatically. All right. So end of Convnets. If you have any questions, let me know. Otherwise, we want to jump into something else. Yes?
I just want to understand the pictures that you showed layers by layers. So how does it being produced, generated? So is it across images that is being learned, trained, or is it?
Yeah, so you train it over all of your images, and then you feed it your new images, and then you say, let me pick the highest 9. So these are 9. So these are 9 activations, right? So you pick the top 9, and you say, let me see in layer 5, when I feed this, what is being passed on to the next layer. So this is what is created in your layer. And read the paper, and it will show you all the details. If you want, we can discuss it more. But let's move on to the next thing. Yes?
How would you handle if images were rotated? If they're like classification?
So there is this is actually very important because an upside down cat is still a cat, right? And Rizal next time will tell us what happens if I take a document and I turn it upside. No, I'm joking. So when you're training, what you have is a set of images, right? And you do a lot of things to your images to make your learned network more generalizable. You do things like you rotate your images, you flip them, you scale them up and down, you shift them, you put them at the center, not at the center. You do a lot of things to them, add noise, not noise, and that is part of your data preparation. FastAI just published a super library that contains everything that you would ever imagine you want to do to your training sets of images to do it automatically for you. You just put it in between your images and your Convnet, and you run them through. It takes care of all of it for you. Check it out. It's useful. Something. I'll share the link later.
Sounds like a data augmentation.
Yeah, but it has a name. And it came out, I think, 5 days ago. I'll share the link in the channel. Yes.
Do you mind if I offer like a few seconds of clarification of the receptive fields that you showed?
Sure.
Okay, so are you picking me up well? Okay, so basically what you see is as you progress through the layers of your network, right, you have this thing called the receptive field. What it means is this activation I'm seeing at layer n, how many and what pixels does it see? What pixels can technically make their way throughout the layers to this activation layer? And why it's limited? Because you're using kernels and convolutions. And because at each layer you're saying what's important to me. And what's called activation, which you get from the previous layers. Anyhow, so you're filtering information at each layer, right? So you end up at n layer and you see a face of a dog. How is that the case? Because they share that same activation cell in layer n. So that, and if they share the same activation, you happen to see all dogs. So your network sees the same thing if they see the same activation. And that's how you classify, okay, these are dogs because they're activating that same cell in layer n. So they're the same thing. And that's how they're classified over there, or clustered together. Does that?
Activation, you mean activation function, right?
Yeah, so the value of each, the value of each component in that tensor at layer n.
Because if it is smaller than something, it doesn't matter. It doesn't make the thing to fire. Yes?
Do you have to identify the amount of layers that you'll have?
Yes. What you do, and that's how you put your name on stuff. What's your name?
Chris.
So you can build ChrisNet. I haven't seen ChrisNet yet. So what you do is that you come up with an architecture that solves a particular problem, and then you fine-tune all of these things that you don't learn. So you have parameters that you learn, like the values of weights and everything else, and biases, but then you have things that you don't learn, and you put together these layers like Legos, right? And then you come up with something that solves your problem better than anyone else, and that's how you get known as the person who built that. And there is research on automating that to build a neural network that optimizes, that designs the architecture of your other neural network to solve a problem for you. It's still research. So, yes.
Just a point of note on the diagram that you used earlier that showed the network. Was that a single path, left to right, top to bottom, or were there multiple paths in there?
The one that I showed is just one path. Yeah. During the training, you do back propagation, of course, but it's one path. And but you can build complicated things that have multiple branches.
And was it just an example, or was it actually this Convnet right here that we're talking about?
No, it was the thing that we are talking about here. But the paper that I have cited in the notes gives you many more examples. All right, so basically you have LenNet, you have AlexNet, you have GoogleNet, you have everything, whatever you can imagine net. These are names of different architectures that do stuff.
And everyone documents them using the same notation that you just showed.
Which notation?
Yeah,
it's called a conv layer and a pooling layer and and you have strides and you have sizes, these are padding, these are all standard terms. That's now you can answer interview questions. You know, what is a stride? What is a pooling layer? What does max pool do when you know? These are all questions that you can easily answer now. Cool.